Today, we present our groundbreaking biotechnology project that addresses two critical challenges: carbon dioxide removal and sustainable waste management in the mining industry. Our project aims to develop an innovative process that utilizes mine processing byproducts as feedstocks to mineralize carbon dioxide from flue gas and recycle sulfur. Therefore, the project tackles climate change and enhanced circular economy. The project innovation lies in engineering cyanobacterial photosynthesis for the simultaneous mineral carbonation and sulfur generation, while developing an anaerobic microbiome capable of following both autotrophic and heterotrophic pathways for gypsum solubilization and H2S production. So let me explain a little bit more about the scientific background underpinning our approach. Mineral carbonation is a natural process that occurs at geological scales, but this represents a promising alternative for carbon sequestration. This can be used, for example, for carbon sequestration from the carbon dioxide coming from flue gas or from gases coming from combustion processes. The process involves reacting carbonate ions with divalent cations to form stable carbonate minerals. Gypsum can provide the divalent cations for precipitating and permanently sequestering the carbon dioxide. The issue here is that this reaction is very, very slow. That's why it occurs at geological scales. So we can accelerate this reaction if we work at temperatures over 300 degrees Celsius or at high pressures that are around 50 to 200 atmospheres. So how can we accelerate this reaction? The reaction is not to be accelerated if we increase the carbon dioxide hydration, which means if we drive the reaction to form bicarbonates in the water. But if we promote photosynthesis, the photosynthesis process actually enhances the carbon dioxide hydration by producing hydroxides in the system, and thus allowing bicarbonate formation, and also thanks to the carbonic anhydrasa enzymes that also accelerate carbon dioxide hydration, and also to the production of EPS in the system. The EPS act as precipitants, regulating the precipitation of the calcium from gypsum to form calcium carbonates. So the idea is to solubilize the gypsum by separating this compound by transforming the sulfate containing the gypsum to H2S or hydrogen sulfide through the action of sulfur-reducing bacteria. And then the calcium that is being released can be used for calcium carbonate precipitation. The issue here is that we don't want to end up with hydrogen sulfide, so we need to transform again the hydrogen sulfide. And the other issue that we have in this ideal scenario is the fact that for a sulfur-reducing bioreactor to be economically feasible, we need cheap electron donors. So here is where we come up with an idea. Why don't we integrate both processes, the phototrophic bioreactor and the sulfur-reducing bioreactor? So this is where the innovation lies in the project. We want to develop a microbiome that contains autotrophic sulfur-reducing bacteria and heterotrophic sulfur-reducing bacteria. The other issue that we have here now is with the phototrophic bioreactor, because H2S is actually toxic for this type of microorganisms. But cyanobacteria are remarkable photosynthetic microorganisms that have demonstrated adaptability to sulfidic environments. They can carry out an oxygenic photosynthesis using H2S as an electron donor. The key thing here of using these cyanobacteria strains is that we can transform the H2S to elemental sulfur. And this is a feedstock that is used in industry. Our project aims to isolate and potentially engineer cyanobacteria strains for enhanced H2S tolerance, ensuring simultaneous carbon dioxide fixation and H2S oxidation to elemental sulfur. So our research focuses on three critical gaps: mitigating H2S accumulation and minimizing cyanobacteria toxicity by using specialized cyanobacteria strains and also by engineering these cyanobacteria strains. The second one is optimizing electron donor availability by creating an optimal, by engineering a microbiome that capable of performing autotrophic sulfur reduction and heterotrophic sulfur reduction. And the third thing is we need to focus on synchronizing kinetic rates and compound flows between the two reactors. And we need to do this by using cutting-edge synthetic biology and microspectral tools. Thank you for your attention.